In this movie, we will derive the so-called deformation equation. It describes the deformation part of a p-wave propagating through a material. The deformation equation of motion refers to the application of the elasticity law of Hooke. This is only one of the equations that describes the wave motion of a p-wave. The other is the so-called equation of motion, and that one is derived in a separate accompanying movie. This is part of an introductory course on reflection seismology. Here we will consider a p-wave that is propagating through a material. On the slide you see a p-wave that is generated from the left-hand side and the wave moves from the left to the right of the material. On this movie you also see a black piece that we will consider here. When we look in detail, when the wave motion goes through the medium and arrives at the little black piece, we see that it gets deformed. We shall consider the deformation and forces working on this little black piece by using Hooke's law on it. So here on this slide we consider that little piece of the movie which we have enlarged. This little piece of material will be subdued to a seismic disturbance. But before we derive the deformation of this piece, let us recall Hooke's law of elasticity. When we consider a spring or a rubber band that is extended, the force F is given as F is minus K times U, where U is the displacement and K is the spring constant. Notice the minus sign since the force is opposite to the direction of displacement. It is a reaction force. Let us now consider the small cube again. The small cube has a volume delta V with sides delta X, delta Y and delta Z. And it has a mass m. And when we apply Hooke's law to this cube, we can express it as P is minus K and then the change in the volume, as you see here on the slide. P is the pressure, delta V is the original volume of the cube, dV is the change in volume of the cube, and K is called the bulk modulus. Note that the cube is only deformed in one direction, so we assume one-dimensional wave motion. Based on this, let us now derive a differential equation using the blackboard. So here you see on the blackboard, you see the cube again. So at one time instant, what we have there is that dV is the change here to the right, so this one. So it's Ux at the place on the right hand side minus this one, so it's minus Ux. And then for the volume we get this side and we get this side. It's multiplied times delta Y, delta Z. So what we're now going to do is we're going to approximate this term because delta X is rather small. So we assume we can do a Taylor expansion of this term here, X plus delta X, as being approximately Uxx, yes, the original one, plus the change, the first derivative following Taylor, and then delta X, the change. Yes, we now can bring this one to the other side, so we get Ux x plus delta X minus Ux x is approximately dux dx delta X. So here you see this term here, yes, that we've got in here. So we can put it in there. So that's what we're going to do. So we get now that dV is approximately dux dx times delta X, delta Y, delta Z, yes, is approximately the change here. And what you see here is, of course, the delta X, delta Y, delta Z. That's the volume of that element. So we can then write is that dv divided by delta v. Yeah, so the change in volume can approximately written as dux dx. So we're now going to substitute this into Hooke's law. Yeah, so we had Hooke's law, which is P is minus K times the change in volume. Yes, and if we now substitute the above, what we get there is P is an approximately minus K dux dx. Yes, typically with land seismic, we do not measure the particle displacement that we hear, because this is the displacement, but we measure the particle velocities with seismic sensors. Particle velocity is the time derivative of the particle displacement. So we differentiate the previous equation with respect to time, which we shall do now. So we do a ddt, we differentiate this whole equation. Yeah, I now take it as being x. So being not, I take it exactly here. I bring this inside, so I get dp dt is ddt on the right hand side, so minus k dx dx. And if we now assume that k is not dependent on time, yeah, then we can write this as minus k ddt, and we get dux dx. Okay, now I would like to apply the rules of partial differentiation, that it's commutative. That means I can interchange dx and dt. So I'll write it down. So if I look to interchange, I can write that d dt of dux dx can be written as, yes, I interchange these two, because it's a rule of partial differentiation. I can write it as dut dux dt. Okay, and we are going to substitute this now into this equation. So what we get there is dp dt is minus k, and now this is interchanged, ddx dux dt. But as you may see here, you recognize here Vx in there. Yeah, because I said that the partial derivative of the particle displacement is particle velocity, and that's the one that we get in seismic sensors. So we can write this as dp dt is minus k dvx dx. Yeah, so this gives the final equation that I want to get to. dp dt is minus k dvx dx, and that's the final equation that I'm interested in, and this is so-called deformation equation. This finalizes the unit on the derivation on the deformation equation as needed to describe the wave motion of a p-wave. This was derived by applying Hooke's law of elasticity to a little piece of material through which a p-wave is propagating. Please be aware that a second movie on the so-called equation of motion exists. This equation is also needed for describing fully the wave motion of a p-wave. Thank you very much for your attention.